So the primary goal of this video is to review the idea of a slope and y-intercept in a linear equation. The other uses include introducing the idea of slope, showing how things are related, such as the table of points, a graph of a line, and a situation. A situation is very similar to a word problem. It also explains how to interpret a slope and y-intercept in a situation, such as a word problem. It shows that a line always has the same slope, no matter which 2 points you choose on the line. And it reviews the vocabulary words y-intercept, slope, unit rate, and rate of change, among other things. Okay, so let's take a look at a sample problem and walk through it step by step. So Mr. Hillsberg's rate of change, and in this blank, we're looking for another vocabulary word that means the same thing as rate of change. And it's the meaning of rate of change when you have a line. So when you graph a line, the meaning of a rate of change is a slope. So a slope is just the rate of change when you graph it in a line. So the word problem is Mr. Hillsberg is walking at a steady pace for a walkathon. He is raising money to help feed the homeless. The longer he walks, the more money his sponsors will donate. His distance from the start line is shown in the table below. So here's the table, and at 0 seconds, he's gone 0 meters. In 2 seconds, he's gone 4 meters. In 3 seconds, he's gone 6 meters, and so on and so forth. If I were to fill this out and follow the pattern, I would notice that at 2 seconds, he's gone 4 meters. At 3 seconds, he's gone 6. So that means in 1 second from here to here, he's gone 2 meters. In 1 second from here to here, he's gone 2 meters. So it looks like he's walking at a steady pace, which is what the problem says. Steady pace means steady rate of change, which means that the slope of the line will also be the same because if you have a steady pace, that means that the slope will not change. Number 1, graph the points on the grid below and connect them in a line. Make sure your line crosses the entire coordinate grid space. So I'm going to go 0, 0. So that's right there because the x coordinate goes first. And then 2, 1, 2, 4, 1, 2, 3, 4. 3, 6, 1, 2, 3, go up 6. And then 4 is going over 4 and going up 8. They said make sure your line crosses the entire coordinate grid space, so I'm going to need to go backwards as well. So you're going to take a ruler, connect those dots, and make sure that your line crosses the whole graph. You should be able to do a better line on a sheet of paper. It's a little harder to draw on a computer. All right, so that's a line and it goes through the entire grid. Mark points, so number 2 says mark points 2, 4, and 3, 6. So 2, 4 is right here, and 3, 6 is right here. Draw a right triangle between the points. So that means I'm going to draw from that point to that point. To even change that color. There we go. Find the rate of Mr. Hillsberg's walking between the 2 points. So the rate of how fast he's walking is how many meters he's going for every 1 second. So when I move over 1 second to the right, so from 2 to 3 seconds, it's only 1 second from 2 to 3, he's going up 1, 2 units. And on the y-axis, that's meters. So 1 second over, because the x-axis is in seconds. And the y-axis is in meters. So when I go 1 second over, I'm going up 2 meters. So the rate is 2 meters up for every 1 second over. So his rate is 2 meters per 1 second. Or you can just write 2 meters per second because anytime the number is 1, we just assume it's 1. So unless the number is different than 1, you don't have to write it. So you can just write 2 meters per second. All right, number 3, mark dots 3, 6, and 4, 8. So we're going to do that again. except between 3.6 and 4.8. There's 3.6, there's 4.8. You're going to want a right triangle there. So there's my right triangle in green. Draw a right triangle between the 2 points I just did. Find the rate of Mr. Hillsberg's walking between the 2 points. So that means from 3 to 4 seconds, that's 1 second, he went 2 meters. So the rate is still 2 meters for every 1 second, which is usually written as 2 meters per second. You can also write it as 2m per second with a slash. All right, so number 4, mark 0, 0, and 4.8. So we'll do that now. So here's 0, 0, and here's 4.8. And they want to write triangle from there to there. Okay. Find the rate of Mr. Hillsberg's walking between those 2 points. All right. So in this case, we're no longer only looking at 1 second. We're looking at 1, 2, 3, 4 seconds. So over the spread of 4 seconds, he's going up 1, 2, 3, 4, 5, 6, 7, 8 meters. So if we want his rate of change, it's going to be 8 meters per 4 seconds. And now, because the number is no longer 1, we have to write it in. So it's 8 meters per 4 seconds. Okay. Now, when we write that down with a 4, if we want to compare it to the other times, we can actually change it to, well, if he went 8 meters over 4 seconds, how much did he go in 1 second? And we can simplify that by putting 8 over 4 and just, so that's 8 meters over 4 seconds, and dividing the top and the bottom by 4. And that turns out to be 2 over 1. So it ends up being 2 meters over 1 second. So 8 over 4 actually means the same thing as 2 over 1. So I'm also going to write that down to make the following questions a little clearer. So these two are the same thing. All right, number 5, pick any 2 points on the line and draw a right triangle between those 2 points. All right, so we've already done those points. So we're going to have to choose different points this time. So we're looking for a point we haven't already used. And again, I'm drawing this very sloppy. I would expect you to do a better job since you're probably doing it on a sheet of paper. All right, so I'm going to pick the points from 0, 0 to 3, 6. So we're going to try that one together. From 0, 0 to 3, 6. So there's my right triangle, and the slant is always with the line. And I'm looking for the rate of change here. So 1, 2, 3 seconds over, and 1, 2, 3, 4, 5, 6 meters up. So that rate is going to be 6 meters for every 3 seconds. And if I simplify that, I'm going to divide by 3 on the top and 3 on the bottom, and I get 2 meters for every 1 second. So it's the same thing. So I'm going to write that down here. It was 6 meters per 3 seconds, which was the same thing as 2 meters for every 1 second. Will the rate ever change on this graph? Well, let's take a look. The slope of the line never changes. The slant of the line never changes. The inclination of the line never changes. So what that means is that the speed of the line and how far it goes up doesn't change because that's the definition of a line. So if I go over 1, it's going to go up 2. So every 1 second, it's going to go up 2. If I went over 1 more and went off the graph, it would go up 2 and go up to 10. So after 5 seconds, he would go a distance of 10. If I went to another 1 step up on that line and I went 2 meters over, it would be at 12. And so because he's going at a steady rate, by definition, steady rate, this steady pace, that means steady rate of change. And a steady rate of change is by definition a steady slope. And that is the requirement of a line. A line always has a steady slope or an unchanging slope. So this rate will never change. Why or why not? It will not change because a line always has a steady slope, a constant slope. All these things mean the same thing. The same slope between any 2 points. Okay. Mr. Hillsberg's rate of walking is called a blank. So the rate of walking is called a rate of change. That's when it's a rate of change is just a number that has 2 units. So a number with 2 units. So in this case, that would be meters and seconds. Okay. When it is graphed in a line, it is called the blank of the line. So you should be able to fill that blank in. You can pause the video if you need a second to remember. And if you filled out the word slope, you're correct. So rate of change is a number. And when you graph it in a line, it's called a slope. Number 7, all the triangles we drew on the graph are related because they are, and this is a review of geometry. If you remembered the word similar triangle, because they are similar triangles, then you're right. Remember, similar triangles all have the same rate. So these all have the same rate. Okay. Number 8, fill in the blank rows of the table above with any new coordinates that are on the line. Mr. Hillsberg, which we did do. So we filled this in with any new coordinates. So if I went up to 7, you would go up by the same rate. So the table would go up by 2 for every 1 second. Okay. Notice that this doesn't go up by 2. This goes up by 4. Why does it go up by 4 instead of 2? So you might want to pause the video and think about that for a second. So the question is, why does that go up by 4 instead of 2? And the answer is because the rate of change is 2 meters for every 1 second. So if you're going up by 2 seconds, which this space is, it's going up by 2 seconds instead of just 1, it should go up by twice as many meters, which it does. So if it's 2 meters for every 1 second, that's the same thing as 4 meters for every 2 seconds. And that's why this 1 point goes up by 4 meters instead of by 2 meters. All right, so next graph. So this is a new problem, but very related. Mr. Hillsberg now takes his dog on the walkathon, holding it on a leash. The dog's distance from the start line is shown in the table below. So this graph down here is, this is the dog's distance from the start line of the walkathon. Graph the points on the grid below and connect them in a line. Make sure your line crosses the entire coordinate grid space. So I'm going to take that 0, 3. So now it's 0, 3, 2, 7, 3, 9. Now I know 9 is not on it, but I can definitely estimate that fairly accurately because it's only one off the grid. 4, 11 is a little harder. So I would not expect you to do that without having a grid, but we're going to try here. 9, 10, 11. So roughly there. And we're going to erase the other points so they don't get confusing. Okay. And that's my line. And it crosses the entire coordinate grid space. All right, number 10, mark 2, 7 and 4, 11. Draw a right triangle between those 2 points. All right, we can do this. 2, 7 and 4, 11. We're going to go to 4, go straight up. It's around there. And there's my right triangle. Find the rate of Mr. Hillsberg's dog between those two walking points. All right, so this is the dog who walked at a different place than Mr. Hillsberg. Remember, Mr. Hillsberg is actually at a different place on the graph. So if I were to just sketch it real quick, he was down here. So his line is a different line. We'll compare the two later. All right, so going back to the dog, we're looking at the dog's rate of change. So from this point in the right triangle, it goes 1, 2 seconds over, and then 1, 2, 3, 4 set meters up, because it goes from 7 to 11. So 7 to 11 is 7 to 8 to 9 to 10 to 11. That's 4 meters up. So that means it's going 4 meters for every 2 seconds, which if you reduce it by 2, ends up being 2 meters for every 1 second, which should be a familiar rate. We're going to write that down right here. We'll write both. 4 meters for every 2 seconds, or 2 meters for every 1 second. All right, number 11, pick a different pair of points on the line and draw a right triangle between those 2 points. And find the rate of Mr. Hillsberg's dog walking between those 2 points. All right, so we're going to get rid of that blue triangle there. And we'll pick let's pick from 0, 3 as our first point to 3, 9. The 3, 9 was up here. All right, my triangles at least are getting better. All right, so they wanted the rate of change between those 2 points. So 1, 2, 3 seconds. So the dog in 3 seconds goes 1, 2, 3, 4, 5, 6. 6 meters. So the rate of change there is 6 meters for 3 seconds. If we reduce that by 3, that will be 2 meters over 1 second. Again, it should be a very familiar answer. So we're going to move that down here. 6 meters for every 3 seconds, or 2 meters per second. All right, will the rate ever change on this graph? So see if you can fill that out. Okay, so you should have written no. And the reason for that is because when we connected those dots for the dog, the rate never changed. It was always going to be for every 1 second over, it goes up 2. Otherwise, the line wouldn't be a straight line, but all the dots are straight that way. And it said that Mr. Hillsberg is taking the dog on a walk, and the dog is going to have to go at the end at the same rate as Mr. Hillsberg, since they're walking together. So why or why not? According to the word problem, because the dog walks at a steady rate with Mr. Hillsberg. A steady rate of change. The rate of change is the vocabulary word for how fast he's walking with Mr. H. Now the graphical reason is, so the graph reason is, why will the rate of change never change? Because a line always has the same slope everywhere. Okay. What is Mr. Hillsberg's unit rate? Well, the unit rate is the rate for every per 1 second or per 1 whatever. So this, if the second part of the rate is 1. So for example, 4 meters per 2 seconds is not a unit rate because that second number is a 2. So that's not going to work. So we're looking for whenever the second number is 1. So if we go back to Mr. Hillsberg's unit rate, 2 meters per 1 second is a unit rate. 2 meters per second is a unit rate. 2 here is a unit rate. 8 meters per 4 second, is that a unit rate? And your answer should be no, because it was, the second number is 4. It's per 4 seconds, not per 1 second. All right, is 2 meters per second a unit rate? Your answer should be yes, because it's per 1 second. So that second rate number is 1 after the slash. 6 meters per 3 second, is that a unit rate? your answer should be no, because the second number was 3, and 3 is not the number 1. So anytime that number is not 1, then you do not have a unit rate. So the unit rate is going to be 2 meters per 1 second, because that's what the answer is for all the questions for Mr. Hillsberg. So what is Mr. Hillsberg's unit rate? It is 2 meters per second. If you write 2 meters, that will be marked wrong, because a rate must always have 2 units. So this one has the unit of meter and second. So if you write 2 meters, that's the wrong answer as well. 2 meters is the wrong answer. Number 13, what is Mr. Hillsberg's dog's unit rate? So let's go back to the dog and check which of these numbers that you see written down are the unit rate. Is 4 meters per 2 seconds a unit rate? If you pause the video and think about that, your answer should be no, because that second number is a 2. Is 2 meters per second a unit rate? And your answer should be yes, because when it says per second, if there's no number, it's automatically 1. Is 6 meters per 3 second a unit rate? Your answer should be no, because 3 is not 1. Is 2 meters per second a unit rate? And your answer should be yes, because there is an invisible 1 with that 1 second. Okay, so the dog's rate is 2 meters per 1 second. Again, if you write 2 meters, that will be marked off, because a rate must always have 2 units. Number 14, fill in the blank of the table above with any new coordinates that are on the line. So if I were to go 1 second, let's go back here. Let's fill in this number right here. If I were to go 1 second, how far would that dog be? You should be able to know that it's because it's between 0 and 2 seconds. It should be between 3 and 7, so it should be 5 meters. At 5 seconds, you should know that it's going to go 2 more from 11, so it's going to be 11 to 13. And at 6 seconds, it's going to go another 2 meters, because it's going 2 meters for every 1 second, so that should be 15 meters. Now, the other thing that these two lines do is compare Mr. Hillsberg's rate of change to the dog's. So I'm going to now graph that purple line from Mr. Hillsberg on the dog's line right down here, okay? So we are going to erase all these other things so that it's a little bit easier to compare. Mr. Hillsberg. And he went 0 meters at 0 seconds. He went 2 meters in 1 second, 4, 6, 8. So Mr. Hillsberg is in purple, and the dog is in yellow. Okay. So notice that the purple line and the yellow line have the same kind of inclination, like how steep the line is. So the purple is the same steepness as the yellow, because the slope is basically measuring how steep that line is. So Mr. Hillsberg's steepness or slope for Mr. Hillsberg, and we use M to stand for slope. And so his slope is 2 meters per second. So slope is 2 without the units, because the rate of change has units, but the slope is just a number. And the dog's rate of change, written here, his slope is also 2. So they have the same steepness. So what's the difference between Mr. Hillsberg and his dog? Well, Mr. Hillsberg started at 0. Whereas the dog started at 0 seconds, he was actually in front of Mr. Hillsberg on the leash. So he was actually at 3 meters already at 0 seconds. So their starting point is different, but their rate of change is the same. So Mr. Hillsberg started, and this number over here, wherever the y-intercept is, that's actually the start point, because that's when your time, or whatever the first number is 0. So whenever the time is 0, whenever the x value is 0, that's your start value. So that number is called the y-intercept. So the y-intercept in a table of points is when x equals 0. So it's always when x equals 0. So we're always looking when x equals 0. In a situation, it's the start point, because it's when no time has passed, start value, or when how much you start with when you have 0 time passing, etc. So this number for Mr. Hillsberg, his start value is 0 meters. For the dog, his y-intercept is 3. So the y-intercept for the dog is 3. So the dog start value is 3 because he started at 3 meters. So the dog's y-intercept is 3, and the dog's start value is 3 meters. Okay. And so we let the letter B usually stand for the y-intercept. So B equals 3 for the dog. And whereas for Mr. Hillsberg, B equals 0, because that's his start value. And that's going to matter more and more when we talk about the equation of a line, which is y equals mx plus b. And that will be another lesson.